Hello everyone and welcome to our seminar series on topological optomechanics. We are looking forward to very exciting talks, as you can see on this screen already. Today we have a talk by Amir, Youssefi and Ewold Verhagen. In total, the seminar series will cover various different topological systems and optomechanical systems. Topological optomechanics is a very rich setting for exploring this because we can explore many-body physics as well as study the impact of gain and loss and nonlinearities coming from the optomechanical interaction. So yeah, I'm looking forward to a very exciting series. So Amir, we'll start with you. Amir is a PhD student at the EPFL Lausanne in Tobias Kippenberg's group, and he's done some very exciting work on superconducting circuit optomechanics, which allows to realize large arrays and explore topological physics. So you have the stage.
Thank you. So let me just share my screen. Okay. Okay, perfect. So hello everybody. I'm Amir Youssefi, PhD student in Laboratory of Photonics and Quantum Measurement in EPFL Lausanne. I'm glad to be here today and share my recent research results on superconducting circuit optomechanics in topological lattices. Before starting my talk, I think my video is a little bit blurred here. No, it should be better. Yeah. Before starting my talk, I can mention that we recently posted our manuscript on archive titled Superconducting Circuit Optomechanics in Topological Lattices. So all the details are also there available. Yeah, let's start with a very brief overview on circuit electromechanics. So we know that the superconducting circuit optomechanics is one of the most successful platforms to realize optomechanics in the past decade. This platform is based on a microwave resonator made out of a lumped element, a spiral inductor or lumped element inductor shunted with a parallel plate mechanically compliant capacitor, where your one of the plates of this capacitors is mechanically movable, and the position of this plate then can manipulate the resonance frequency of your microwave resonance, and this will allow you to have optomechanical interaction between mechanical mode and the microwave one. At the heart of this system, you always find these nice mechanically compliant capacitors. As you see here, geometries are very different, realized by different groups among the world, but I would say the fabrication process or the way that we are making them is more or less similar in different groups. And we can mention a few important examples of physical phenomena realized in this platform, such as ground state cooling of mechanical motion, quantum squeezing of the mechanical motion, realizing non-reciprocity using optomechanical interaction, microwave non-reciprocity, and also entangling distance mechanical oscillators. And for sure, lots of other works that I didn't mention here. But the important thing here is that almost all of this phenomena and these results discovered in this platform were investigating only single mode optomechanics, or at max two mode optomechanics. However, we know that if we can scale up optomechanical systems to realize optomechanical arrays or chains, there is a very rich physics beyond. So people already studied a lot in this field, and there are several theoretical proposals showing collective dynamics, existence of collective dynamics or topological phases, quantum many-body dynamics, Anderson localization, as well as quench dynamics, to name a few, in the optomechanical arrays or optomechanical lattices. But what is the challenge? What was the problem to realize experimentally these systems? That challenge is mainly coming from the technical side, coming from the microfabrication, nanofabrication process that we use to develop and to fabricate these mechanically compliant paraplate capacitors. So in the conventional, or I would say traditional process, you always have your mechanically movable plate defined as a non-flat in a non-flat geometry. So you can define your bottom plate of your circuit and then cover it with some sacrificial layer, and then define the top plate on top of the sacrificial layer and remove the sacrificial layer to release your capacitor. But because of this non-flat geometry, when you cool down these devices to cryogenic temperatures that we need to operate in, we see a huge deformation in the geometry of this plate, which reduces the gap size down to tens of nanometers. But unfortunately, it's not predictable. So we cannot have a good control on the final gap size we achieve at low temperatures. And then you can imagine if you fabricate lots of these devices on a chip with a very similar process, at low temperatures, you cannot expect to see similar properties on this in this paraplate capacitors. So this was the most important challenge to scale up these systems. So what we proposed, we suggested to change this process flow in a way that we etch down our substrate to define a so-called trench, and then define the bottom layer of our circuit inside this trench and cover this trench with a sacrificial layer, planarize it, and then define a flat top plate as a movable part, as the movable part of our optomechanical system. This flat geometry then ensures us at low temperature to have a very well controlled gap size in our paraplate capacitor. Of course, at room temperature, it can still buckles up, but when you cool it down, you have huge tensile stress in your superconducting thin film, and this will guarantee the gap size you designed for. So with this process, we fabricated the new generation of superconducting circuit electromechanical systems. Here you see an example of a building block, of an electromechanical building block, I would say, made out of aluminum. So here you see the spiral inductor shunted with this drumhead paraplate capacitor, which is suspended over a shallow trench in your substrate. So here you can see a more zoomed in SEM image of the clamps of this drumhead capacitor. You can also see a focused ion beam cross-section image, which shows a perfect planarization of the top plate. And yeah, then we see that this drumhead resonator can support megahertz range mechanical frequencies, and the microwave circuit can support gigahertz range microwave frequencies. So with this nice building block, now we can imagine making one-dimensional optomechanical chains, or even two-dimensional optomechanical lattices, by introducing a microwave coupling between the microwave modes in this system. So we still keep mechanical modes isolated. They are just coupled to their own microwave mode in every individual site, but then we introduce microwave mutual couplings between the microwave modes. So in this case, we can easily write down the Hamiltonian of the system as sum of the individual optomechanical Hamiltonians of every site plus the coupling terms between the microwave modes, which are connected to each other. And then this Hamiltonian can be easily diagonalized by just transferring from, by just applying a transformation on the basis of our Hilbert space. So we go from the bases defined based on AIs, which are modes in individual sites, to the collective modes of that structure, which are basically eigenvectors of our system. So in this case, we can rewrite our Hamiltonian based on the collective microwave modes in such chains or lattices, which are now not coupled to each other, and then we see that now every mechanical mode in such a chain or lattice can, in principle, be coupled to all microwave collective modes in the system. And this coupling rate now is modified by the mode shape of the collective mode we have in the system. So a mode shape I denoted here by psi ki, which is the mode shape of collective mode k at the site I, and psi ki squared is just the energy participation ratio of individual sites I, physical site I, in the collective mode of k. So we can look at an example here. We just chose the standard SSH model, which is the simplest model we can imagine to have a non-trivial topological property. It is very well-known model. We have our individual optomechanical sites, and then we introduce nearest neighbor microwave coupling between neighbor sites, and we alternate this coupling side by side. So we have couplings of J and J prime, J and J prime. And if you solve the energy diagram of the system, you can see that this energy diagram contains a lower pass band, a higher pass band, and in special circumstances when J over J prime is smaller than 1, then we are in the topological regime. It means that we have two isolated topological edge states in the middle of the band gap, we can look at the collective mode shape of that structure. So we can see a few mode shape examples in the higher pass band, lower pass band, and also topological edge states where we have localized mode shapes on two edges of that structure. Now we can excite phonon-photon transitions between the mechanical modes, different mechanical modes, and the collective modes in this system by applying a proper pump to a dedicated to a specific collective mode that we want to excite. So this system we just realized using our electromechanical building blocks. So here you see a tensile chain of electromechanical resonators coupled to each other. Every site is coupled to its neighbor through mutual inductance, which can be controlled by the physical distance between these big rectangular spiral inductors. And we designed this circuit to operate in the topological regime of the SSH model. And then we can read out and control this chain by coupling it to two coplanar waveguides on two edges. And here you can see the circuit schematic of this chain that we realized. So Of course, we operate this experiment at millikelvin temperatures because we have superconductors, and also we want to have very clean microwave background. Our our frequencies are much lower than the optical frequencies, so we need to operate in cryogenic temperatures. And if we look at the microwave transmission response through this chain, we can clearly see 4 modes in the upper passband, 4 modes in the lower passband, and our 2 topological edge states in the middle of band gap. After that, we can choose one of these collective microwave modes of the system, apply a red detune pump on it, and do optomechanical induced transparency experiments by sweeping a weak probe over the resonance. With this, we can see exactly 10 different optomechanical induced transparency features, which are corresponding to different sites along this chain. And as you see here, we intentionally incremented a little bit the trench radius of this drumhead capacitors site by site to induce an intentional shift in the mechanical resonance frequencies. This will allow us to exactly determine every physical site by its mechanical frequency in next experiments I'm going to show you. So now we can use optomechanical interaction as an embedded probe to measure the collective mode shapes, collective microwave mode shapes in such a structure. And how it works, it's very easy. We know that our mechanical modes are coupled to the collective modes with a coupling rate, with an optomechanical coupling rate, which is now modified and proportional, and is proportional to the mode shape, to the collective mode shape of that mode. So we can just measure the optomechanical damping rate, effective optomechanical damping rate, and then this ratio between the damping rate and the intracavity photon number we have in a collective mode will give us some information on the mode shape. So what we can do, we can select one of the collective modes. We can apply a red detuned pump to it using a very simple time domain protocol. We can selectively excite each of these mechanical resonators, and then measure the ring down, the energy, the ring down of the energy of this mechanical oscillator. And here you see that, for example, for a specific mechanical oscillator on a specific microwave collective mode, by increasing this red detune pump power, we see that the optomechanical damping rate is getting increased. Now, if we do this experiment for different sites in this chain, we see that the dependency between gamma effective, the relation between gamma effective and the power, which defines this slope, is now different and proportional to the mode shapes of this collective mode. So if you are doing this experiment on a mechanical mode, which is more strongly coupled to the collective mode shape, you see higher slope. Based on this information, we can exactly extract all the mode shapes of the collective mode shapes of this tensile structure, as you see here, the measured values and the theoretical predictions. You see they are in a well agreement with each other in the upper passband, lower passband, and also the topological edge states when we have localized mode shapes on 2 edges. With this information, we have all the eigenvectors of our microwave Hamiltonian plus all the eigenvalues, which are nothing else than the resonance frequencies of the collective modes. So with these 2 information, we can in principle reconstruct the full underlying Hamiltonian of the system. So here you see the reconstructed Hamiltonian, experimentally measured Hamiltonian of the multimode system in the rotating frame with the frequency of with the average frequency of individual microwave sites. So on the diagonal elements here are showing the disorder, the actual disorder in our microwave frequencies, which is showing less than 0.5% disorder in our microwave frequencies. Also, you can see the alternating nearest neighbor couplings between adjacent sites here. And beyond this nearest neighbor coupling, we can also experimentally measure the second nearest neighbor coupling and third nearest neighbor coupling, which are caused by the parasitic mutual inductance between distanced LC resonators here. So we can also extend our platform to 2 dimensions. So we can here we designed a 24-site 2-dimensional honeycomb lattice, honeycomb optomechanical lattice. And even to make our system a little bit more neat, we inspired from the SSH, the standard SSH model, we decided to alternate the couplings, microwave couplings in 2 different directions in this lattice. And this, you can easily show that this will result to have a similar non-trivial topological property in this chain. So to see the lower passband, upper passband, and topological edge states in the middle. So this is the realized system. You can again look at the microwave transmission of this system. We see exactly 10 modes in upper passband, lower passband, and 4 modes for edge states. Then we can do ohm experiment. Exactly, we can link every mechanical frequency to this position in this lattice, and using the same technique, we can measure the collective microwave modes of this structure. Here as an example, I'm showing a few modes in the upper passband, lower passband, and also topological edge states, where you see your mode shape is localized on 2 edges of this honeycomb lattice. Also, we can again reconstruct the Hamiltonian of this 24 4-mode system. So here you see the experimentally reconstructed Hamiltonian and the design Hamiltonian, theoretical design Hamiltonian, considering second nearest neighbor couplings. And you see they are in a nice agreement with each other. So with this, I want to conclude my talk. We realized we showed a new platform to scale up optomechanical systems in the superconducting system, in the superconducting circuit platform and microwave domains. And we realized 1D and 2-dimensional optomechanical lattices, and also introduced a new technique to measure the collective mode shapes in that structures. As an outlook, I can mention that we can demonstrate for sure in future collective dynamics and synchronization dynamics in that lattices. Also, in another work that I didn't talk about it today, we showed that we can cool down these mechanical oscillators down to 3% occupation, grounded occupation, so 0.03 occupation in the mechanics. So we expect to also be able to see in future highly entangled quantum mechanical states in such lattices. And also we are trying to integrate this platform with superconducting circuit qubits. And this probably will allow us to investigate quantum simulation protocols in future using this platform. With this, I want to thank you for attention. And also thanks my colleagues here in LPQM, especially my advisor, Professor Tobias Kippenberg, and also our funding agencies. Thank you very much. I will be happy if you have any questions.
Thank you very much, Amir, for the great talk. This is really impressive. Do we have any questions? Maybe I can ask one in the meantime. When you showed the microwave collective modes, you showed that there are some topological edge states. Can you extract something similar for the mechanical degrees of freedom? Can you also?
You mean the Hamiltonian? You mean, or the?
This was for the microwave field, right? So
yes. So the thing is that here in such a structure, we always operate in a regime that is far away from a strong coupling regime. So the optomechanical coupling rate is much lower than the microwave mutual couplings between microwave modes. So it doesn't appear seriously in the dynamics of our system. But for sure, in future, if we can introduce also a mechanics to mechanics coupling, so direct mechanical coupling between modes, then probably we can also investigate more serious, I would say, topological properties.
That sounds very exciting. Thanks. Mudassar has a question. Yes, go ahead, please.
Thanks, Amir. That was a really, really amazing talk. Actually, I learned a lot. Thank you so much. There was when you started to talk about damping that's experienced by the different mechanical modes, there's an aspect I didn't quite understand. I was just wondering if you could go back to that slide.
Yes.
So this one here.
Yeah.
So why is the damping greater? So this is environmental damping, is that right? The gamma that you're talking about here?
Yeah, this is the optomechanical damping rate. So your bare damping rate of your mechanical oscillator is always constant, but we know that we can effectively damp our mechanical oscillator through optomechanical interaction. So if you have your mechanical mode coupled to one of these collective microwave modes, by increasing this coupling rates, okay, you are coupling your mechanics more to your microwave bath, which is very cold bath, instead of coupling it to your mechanical bath, and this this can reduce the occupation of your mechanics, but also increase the damping rate, energy damping rate in your mechanical oscillator.
Does that not have adverse effects for the other? So you're focusing on a single mode when you're increasing the power of your.
Yes.
Right?
When you increase power on one microwave collective mode, the other mechanical modes are also getting damped, but we are measuring just one of them in every single experiment. They don't interfere with each other because mechanical modes are not coupled to each other here.
Yeah, that's what I was. Okay, thank you.
Thanks.
Ewold, I think you had a question.
Yeah, thanks for the great talk. I have two questions actually. One very practical one. Your drums are pretty large compared to previous experiments that I know of. So I was wondering if you do that intentionally.
Somehow, yes. Okay, they are not actually that larger, maybe factor of 2, but now our mechanical frequencies are around 1 megahertz, 2 megahertz. If you make them smaller, then you will have higher mechanical frequencies. But yeah, the reason is that we are also looking for low mechanical damping rates, and then we know that the mechanical quality factor is scaling with R squared, with 1 over R squared. So larger drum, much higher quality factors.
And if I may, about your outlook, do you see any application of these kind of topological microwave states for things like entanglement or computing, what you mentioned?
Okay, actually this is a toolkit that can be used to investigate different theoretical proposals. But we know that if we really want to, for example, do some serious quantum simulation in this system, then for sure this design, this mode diagram, when your mechanical modes are isolated, will not work. We need to have mechanical modes coupled to 2 microwave modes in the middle. Then in that case, if you also have a superconducting qubit coupled to one of the microwave modes, we can prepare some quantum state using the qubit, transfer it to the mechanical to the microwave field and the mechanical oscillator, and then by applying a pulse train, you can start to manipulate this quantum state in the mechanics in different mechanical modes and transfer it and do some quantum simulation protocols there. But yeah, for sure you need nonlinearity.
Okay, Tooth, I think you're next.
Yeah, thank you. It was a very nice talk.
Thanks.
So I have a question. For the 2D case,
yes,
you show that you have localized states at the boundaries, but have you also tried to have traveling edge states? Is it the case because the model is too small to display traveling edge states?
Yes, actually, here there is no PT symmetry breaking. So here it's very similar to the 1D SSH chain. And the only difference is that, okay, we have more degrees of freedom. So for sure we cannot show a traveling edge state like for example, yeah, like systems that you have PT symmetry breaking there. Yeah, so it's different.
So one can also have traveling edge state just by varying the link strength. So what you are exactly doing, but maybe slightly more complicated scenario, but one still have to vary only the link strengths. So I was thinking it should still be possible with your system.
Yeah, it is possible, exactly like your recently posted manuscripts at yours. There you have coupling between mechanical modes and also optical modes. Yeah, and this will let you to to have a specific a direction to for these traveling edge modes. But here the mechanical modes are not coupled to each other at all. So this is just a simple microwave.
No, I mean like
microwave modes. Yeah,
traveling mode for the microwaves, not for the.
But then you need to have some. You need to have some. Reference for your time. I mean, I don't think in this structure we can have traveling edge modes, but maybe we can discuss later more.
Okay. Mm-hmm.
Yeah.
Thank you.
The discussion is really interesting, but I think we have to move on. If you have any further questions, maybe you could put them in the chat, and Amir, you could reply them there. Would that work?
For sure.
So then let's move on to Ewold's talk. Thank you very much again. We really enjoyed your talk.
Thank you.
Ewold, while you're getting ready, let me introduce you. Ewold leads the Photonic Forces group in the Center for Nanophotonics at EMOF and is also a part-time professor of applied physics at Eindhoven University of Technology. And his research focuses on light-matter interaction at the nanoscale. And quite recently, he's also working on topological physics of light and sound. And we're very much looking forward to your talk.
Yeah, thank you very much, and thanks so much to you and organizers for this invitation. It's nice to present some of our recent experiments here. This work was really performed by the bulk of the work was performed by Javier Del Pino, Jesse Slim, and John and Matthew in my group in Amsterdam. And so I want to talk about different kinds of routes of using optomechanical interactions to create topological or induce topological physics for both light and sound, focusing in particular on nanomechanical topological insulators. And since this is a session that is on topology, and maybe not all of you are as familiar with it, I would like to start with saying a few words on that, even though any introduction that I give cannot do justice to the richness of the field of topological physics and topological phases of matter in particular. But there's a lot of interest, of course, in the past decades, and it's also clear why it's simply fascinating to see how the deep mathematical description of a material or a system can give rise to and explain so many intriguing phenomena. And also from like an application point of view, of course, one of the hallmarks of topological insulators is that they can inherently protect some useful functionality, like conduction in an electronic topological insulator against imperfections. And I mean, to say it jokingly, if I could take a bagel or a pretzel, and if I could uniquely protect its perfect taste just by counting the number of holes in that pretzel, of course, this would revolutionize the field of bakery, and I think that's what it's done also to physics. All jokes aside, if I say a bit of what we mean with a topological insulator, without going into too much detail, if one can describe a material and define on the states of that material, on the band structure that describes this material, some quantity, that can only be evaluated to integer values. This is then a topological invariant that if the material is insulating, if it is gapped, we know that this invariant can only change if that gap is closing. So if I morph a material from one to another, and such that it changes the topological invariant, I know that actually it must stop insulating somewhere in between. And so then the interesting thing happens when you combine two materials with different topological invariant, because then nature needs to solve the ambiguity at the interface, and it does so by allowing a state, and that state then is necessarily there because of the topology of the materials that it bounds. And this is these famous edge states, and they are, as I said, necessarily there, so they are protected by the topological nature of the materials, and this gives rise to things like robust conduction, etc. Now, so that means that these states are immune to all kinds of imperfections, scattering. Now that's appealing, and it happens in many different kinds of material systems. These are perhaps the most famous ones. The quantum Hall effect, on the one hand, here a magnetic field breaks the time reversal symmetry for electrons in a two-dimensional electron gas, and that means that while this two-dimensional electron gas is insulating in the bulk, actually at the edge it is conductive, and this is the conductance that is famously quantized in the quantum Hall effect. And you can very hand-wavingly see how this comes about by seeing that the magnetic field makes these electrons go into cyclotron orbits that are closed in the bulk, but at the edge they cannot be closed, and so the electron will skip along the edge and be transported in a direction that is controlled through the magnetic field that breaks the time reversal symmetry. Now, in another class of topological insulators, the quantum spin Hall effect, this does not require a magnetic field, but here you can have spin-orbit coupling that creates an effective magnetic field that is opposite for opposite spins. And so you basically have two copies of the quantum Hall effect, meaning that each spin propagates in an opposite direction along this edge. And you have two edge states, but they are also protected. In this case, they're protected, in fact, by the time reversal symmetry of the system. And this is owing to the fact that these spin 1/2 particles, that they exhibit Kramer's degeneracy. Now, if you want to construct a topological insulator for bosons, photons, or phonons, then in fact, that Kramer's degeneracy is not there. And in fact, there you also have a challenge in realizing the quantum Hall effect, because photons or phonons do not naturally interact with a magnetic field. So you need either to effectively break time reversal symmetry with some trick, or you can make use of spatial crystal symmetries that have some analogy to the quantum spin Hall effect, where then a crystal symmetry protects edge states and induces them. And so, of course, in the last decade, many people in all kinds of regimes have sought to realize and manage to realize bosonic topological insulators in the photonic domain, from microwave to optical frequencies, and from helical waveguides and resonators to small photonic crystals. And also in the mechanical domain, using, for example, arrays of smartly coupled gyroscopes, coupled pendula, small piezoelectric materials, etc. By either using one of these tricks that I mentioned before. And it has also been proposed to use optomechanics in this context. And so why would you do that? Well, for one, the active control that one gains with optomechanical interactions makes optomechanical systems highly reconfigurable through laser drive fields. You can use it to very effectively read out topological states and map them in space and time. And it could bring topological insulator physics to domains of nanophotonics and nanomechanics in particular that have also interesting applications. And then maybe most importantly, optomechanical interactions could induce themselves topological phenomena that either mimic those in electronic domains, some specific ones, or induce topological phases of matter that maybe do not have an analog in the electronic domain. Now, we've already seen some wonderful experimental progress along various of these lines. And in fact, we just saw an example of this exquisite readout using mechanical resonators to read out, sorry, that's this slide, to read out the topological states of a microwave field. And I hope that, that next week we get to hear something about this kind of experiment where you have a large array of mechanical elements that form through, again, such a symmetry-based protection mechanism, topological states that can then be very accurately read out with optical fields. Now, those are fantastic results, but I want to also discuss now with you some routes into actually using the optomechanical interaction itself to break time reversal symmetry, because that is nicely possible with optomechanical systems, either for light or for sound. Because on the one hand, mechanical motion of a mirror can modulate in time an optical cavity field, and vice versa. Radiation pressure in this cavity can have or exert a time-dependent force on the mechanical resonator. And such time-variant potentials in a right system can effectively break time reversal symmetry. So this gives access to the kind of physics of the quantum Hall effect that I mentioned earlier, mimicking the action of magnetic fields. And so I would really like to emphasize at this point also, if you haven't seen Vittorio Piano's talk of last week in this seminar series, then I would encourage you to look it up on YouTube, because he goes into much more detail there as well. So I want to share with you some of our efforts and ideas into, well, doing exactly this, breaking time reversal symmetry for phonons in nanomechanical lattices. And then in the second part of the results I would like to share, we try to actually go beyond mimicking the quantum Hall effect and seeing if, when we go to so-called non-Hermitian systems, we see effects that do not have a counterpart in electronics. All right, so let's get into it, and let's first try to understand how this magnetic fields and the way that they break time reversal symmetry, how that induces this quantum Hall type behavior. And for that, you can appreciate that an electron in a magnetic field, when it travels a certain path, it gains a phase, and that is proportional to the vector potential along that path. And so one nice model for the quantum Hall effect, the Harper Hofstadter model, for example, describes that by imagining this two-dimensional electron gas as a lattice of sites on which particles or excitations can hop from one site to another, gaining a phase that is opposite in the opposite direction, just like this the magnetic field does for an electron. And then if you control in the phases of all of these links in such a way that each of these square plaquettes in this lattice has a total round trip phase, capital phi here, this has an analogy to the propagation of electrons in a ring that is also called the Aharonov-Bohm effect. And that phase along the total loop is proportional to the magnetic flux, and that is piercing this loop of sites. Now, this description that as I mentioned, shows you how basically the Aharonov-Bohm effect can be seen as the basic ingredient of the quantum Hall effect when you extend this to a lattice. And this also shows how you could go about creating quantum Hall type physics on a lattice of resonators, for example, which are these sites then. If I manage to somehow control the hopping from one resonator to another with a phase that depends on direction. And so that is the goal, and that is possible with optomechanical interactions. And one way that this is possible is when you take a laser that is red detuned from an optical cavity. As you may know, this laser can stimulate the coupling of a photon that is resonant with the cavity and a phonon in the mechanical resonator, basically converting the frequency of the photon to the mechanical frequency with the help of the pump laser frequency. That's exactly the difference of these two. And then importantly, the phase of that control field is imprinted on this transfer from the photon to the phonon. And you'll see that because this rate here is that couples the photon and phonon degrees of freedom is complex, and that also means that for the reverse process you gain the opposite phase because it's the Hermitian conjugate process. Now, you can start constructing loops if you have two optical cavities that are both coupled to a mechanical resonator, for example. Now, one control field of one cavity can stimulate the conversion of a photon in this cavity to the mechanical resonator, gaining the phase of this control field. But then the other control field can turn that phonon back into a photon in the other cavity, gaining the negative phase of the second control field. Now, if you go in the opposite direction, of course, you gain exactly the opposite total phase. And so by playing with the phases of these control fields, you can, for example, create a pi/2 phase in one direction and a minus pi/2 phase in the other direction. It's a maximal difference that you can get. And this clearly breaks time reversal symmetry. And all you need to do to still close that loop and really create the kind of effects that you see in the Aharonov-Bohm effect is to still couple these two optical modes somehow together in another way, and then this closes the loop. You can gain a finite total phase that is independent of gauge that pierces this loop, and that you can call a synthetic magnetic flux. And this you can use to create interference effects that also break time reversal symmetry and create useful functionality, like blocking the transport of light in one direction and allowing it in the other. It's called isolation. And that indeed has been demonstrated in various optomechanical systems a few years ago. That all can be described by multiple optical modes coupled via mechanical resonators. And in some systems, you can very clearly identify this, also in multiple LC resonators, for example, coupled to a membrane. We have studied mostly ring resonators in the past. There, it's maybe a little bit harder to directly recognize that there are two optical modes in play. But you can recognize that if you consider that any ring actually always has two optical modes, if the ring is perfect. You can say a clockwise and a counterclockwise mode, but also the superpositions of these, the even and the odd mode in the ring. And these are both excited by a control field that comes in from one side, exactly with, in fact, the pi/2 phase difference that creates this maximal asymmetric phase. So this really establishes a kind of a synthetic magnetic field, a Hanon-Bohm effect, if you will. And you can use that by smartly using also dissipation in this system to let light be transmitted in one direction and blocked in the other. Or if you configure it to multiple waveguides to create really a circulator for photons, that by using the coupling to the mechanical vibrations of this ring, photons in port 1 will exit at port 2, and 2 will exit in 3, 3 to 4, etc. Now, you can imagine in the topological context that you can use these kind of gauge fields, these magnetic vector potentials, if you will, coupling optical to mechanical modes to create, at least on paper, lattices that are really described by these synthetic fluxes, and that should exhibit the quantum Hall effect and break-time reversal symmetry. And in fact, this was proposed for the first time by Vittorio Piano and his co-workers, and they also showed a possible way to implement this in a photonic crystal domain. It's not exactly the same lattice that I showed in this cartoon before, but it works exactly because of these effective fluxes that you imprint through optical drive fields. Now, there's a challenge, however, which is related to the fact that for this to work, you need these optical cavities. The optical cavity line is to be smaller than the mechanical frequencies. You need to be in the resolved sideband regime, and you need to have many of them that all have the same frequency to within that precision. And that's a huge challenge, as we actually just heard. And so we set out to but if you do that, if you manage to do that, then you really expect to see, both for optical excitation and for mechanical excitations, quantum Hall type behavior, where if you excite it, it will be one of the resonators, here, one of these circles here, an excitation will be guided along sharp corners, like in a topological insulator, and only in one direction, that's governed by the effective magnetic field piercing this lattice. Now, I mentioned these challenges, and this is the way we thought about this is that, okay, let's see if we can construct similar physics, but now in a system that does not need this resolved sideband regime. And the way that we approach this is that we create a coupling between mechanical resonators assisted by an optical field, but outside this resolved sideband regime. And how this can go about is that if I suppose that I have two mechanical resonators that are both coupled to a single optical mode. If I have a detuned laser, then one of the resonators' vibrations can, of course, change the intensity in the cavity, and that changes the force that acts back on this resonator. This is the so-called optomechanical spring effect. But it also changes the force on the other resonator. This you could call a cross-mode spring effect, and that means that it establishes a linear coupling between these two mechanical modes. Now, the system that we use is this so-called sliced photonic crystal nanobeam system. This features very strong optomechanical interactions, so you don't need a lot of optical power to actuate and couple these two halves of the beam to each other via the light fields that are squeezed in the gap between these beams. So you can use this at low power, and or differently said, one can already achieve this for relatively broadband optical cavities, which is a benefit for scaling to larger systems. So. But now, how do we still implement such a gauge field like we saw before, and non-reciprocity or breaking of time reversal symmetry? And for that, we use the following trick. We take two mechanical resonators that are in fact of different frequency, and then to couple them, we will modulate the optical intensity at the frequency difference of these two beams. You could say that then the modulation sideband of one beam's vibration in the cavity will be resonant with the other beam, still establishing this force, or you can see it in a frequency domain as saying that you basically have two tones that allow to match the frequencies to each other. And then in a suitable rotating frame and adiabatically eliminating the optical modes, you end up with a Hamiltonian that is really just a beam splitter Hamiltonian, but where A1 and A2 are here the annihilation operators of two mechanical modes at different frequencies. And they're coupled via a rate that is proportional to the size of the spring effect in this system. And the modulation phase, phi, that is now imprinted as a gauge field or as a Peierls phase on the transfer of a phonon from one resonator to another and back. So that is what we will exploit. But first, let's see if we can actually couple these two mechanical beams to each other. So now they have different lengths on purpose. It means that they have different frequencies. And now we switch on this modulated laser beam. And then with another laser, we read out the thermal motion of these beams at the same time. And then you see that both of these resonances split. And that is because, in fact, they are coupled to each other. So this is a feature of strong coupling. And the new normal modes of this pair of beams is kind of a Floquet mode. It is a superposition of one resonator at the first frequency and another resonator at the other frequency. And so that's connecting the lower peak here to the lower peak there, and the upper to the upper. We couple the light in and out of the sample just from free space, in fact, because the cavity is designed to couple a little bit to the normal incidence. Okay, now, if you have such coupling, then you can, in principle, imagine constructing lattices out of these resonators. And this is how one proposal that we did for how one could go about constructing the such a lattice, in which you can then imprint the quantum Hall phase. And so what you see here is these nanostrings that are, each one of them is actually coupled to three neighbors through optical cavities that one could illuminate. And if you control the phases with which the light field is modulated, you need a few different phases. But if you do that, then one expects a quantum Hall like edge state, and this is a simulation of what it would look like if you had a large lattice of resonators where you would excite one of them at the edge. It would also propagate along it. And here we put in, because we're experimentalists, we put in realistic amounts of disorder and losses, as well as the coupling rate that we can actually induce in these kind of systems, which, owing to the large optomechanical interaction strength, can be much larger than the dissipation rate, meaning that it can propagate from any sites. The advantage is that this can work in the bad cavity limit in principle. Now, still, of course, it's a pretty large challenge to construct all these optical cavities and to illuminate them. One thing that one can be helped with is that in fact, one can use multiple mechanical modes of a single string. Since we're anyway coupling modes of different frequencies, and any string exhibits higher order harmonics, we can use higher overtones of these mechanical strings as degrees of freedom in a lattice. And so in the following experiments, we will do with, in fact, 3 mechanical modes, just scaling up the complexity a tiny bit. And so to see the basic effects of when we couple these 3 modes in a ring. And now we imprint through 3 coupling tones and 3 phases that we put on our electro-optic modulators. We imprint a flux piercing this loop. And then if you do that, you see the following. These are the thermal spectra, again, of the of one of the 3 resonators. In fact, you see that it's split in 3 because of the strong coupling between these resonators that we induce. And then when we vary the flux, you see that the frequencies tune, and they do it exactly as you would expect for a magnetic field. In fact, for a triple quantum dot in a strong magnetic field. Now, one thing that you can also appreciate is the fact that this imprints a helicity or chirality on the transport in this system. And so that is nicely seen if you drive one of the mechanical resonators with resonance frequency and then switch off the drive, switch on this interaction, you see that for a particular flux, for example, pi/2 here, you see that the energy really hops in a chiral fashion among these resonators, exactly like we know it happens in the quantum Hall effect for these edge states. Here, this is of course a microscopic element of it, consisting of only 3 resonators, and this constitutes a phonon circulator, if you will, induced by the optical drives. Now, what I want to do next is see, okay, can we now also induce interactions that actually do not directly have an analog in the electronic domain, in the quantum Hall insulator, and that we do by introducing squeezing interactions. And this relates to a huge field, active field of research, which is about non-Hermitian topological insulators. Non-hermiticity means that we introduce gain and loss in a smart way. And so there has been a lot of work on this, in fact, including by our chair, on understanding, well, first of all, what happens to topological states if you include gain and loss, but also by doing that, can one expect new phenomena and new phases of topological phases of matter that exist because we control the dissipation in the systems. Of course, this is complex to think about, literally, because the eigen energies become complex in a way as soon as your system is non-Hermitian. But there may also be interesting applications. People have considered and demonstrated lasing into topological modes, which is of course a non-Hermitian phenomenon in itself. There have been proposals of how to enhance sensing in systems based on these kind of principles. And like we heard last week from Vittorio also, he proposed how to build, for example, a topologically protected amplifier, even down to the quantum domain. And he did that by introducing squeezing interactions. That is, parametric control parametric amplification and induced damping in such a system to give it a non-Hermitian character and also a topological character. Now, so I want to show, well, first of all, how does squeezing anyway introduce non-hermiticity? Well, a squeezing Hamiltonian adds to any beam splitter interaction particle non-conserving interactions, right? That are the pairwise generation or annihilation or generation of excitations, either in a single resonator, it's one mode squeezing, or in two different resonators, two mode squeezing. And the parametric gain eta also can have a phase that we can use to control. Now, why does this give rise to, how does this give rise to non-Hermitian dynamics? Well, you can, starting from this Hamiltonian, even though this Hamiltonian itself is Hermitian, if you write down the equations of motion in a matrix form, you can recognize a dynamical matrix if you that describes the equations of motion for independently the annihilation and the creation operators. And that dynamical matrix, in the presence of squeezing, is in fact itself non-Hermitian, and the eigenvalues of the dynamical matrix, they are the natural excitations of the systems, the normal modes, if you will, and these can be generally complex and describe non-Hermitian dynamics. Clara, how much time do I have?
Maybe 3-4 minutes.
Okay, I'm going to speed up. So we do that simply by modulating the optical field at the sum of the resonator frequencies, either introducing single mode or two mode squeezing by doing so. And so the first thing that we see if we take our trimer again, but now introduce two-mode squeezing, is that there's in fact, although for a particular value of the coupling rate, the spectra look similar, there's now an interesting asymmetry between the amplitudes in this in resonator 1 and 2 here. And this asymmetry, this localization of energy, cannot happen in an Hermitian system. And it's controlled again by the flux that is now given by both the squeezing angles and the beam splitter phase. Now, another thing that that one can see though in these systems is that is the introduction of so-called parity-time symmetry. And for that, I want to very briefly say what that is the basic phenomena of that parity-time symmetric systems are known for. Is this, if I take the canonical system of two resonators where one has loss and the other one has gain, then the spectrum of this can be real, but beyond a certain amount of gain, the states of this dimer can spontaneously break symmetry and become complex. And this has gained a huge interest because of various applications. And also this has been predicted you can do with squeezing interactions. And so we do that in a minimal system that now contains only two resonators that we couple via a beam splitter interaction, and we drive both of them individually with parametric tones. And what you see then is that indeed you can squeeze the thermal motion of these resonators, but now the squeezing varies or is controlled by varying any of these phases in the resonator. And in fact, one can recognize a single gauge invariant flux again that controls the amount of squeezing. So how can we understand this? Well, we can in fact again interpret it in terms of a loop that is pierced by a flux. If you now realize that this squeezing interaction you can understand as basically the simultaneous creation of two excitations. You can understand as the annihilation of an antiparticle and the creation of a particle. So it's a conversion of a whole into a particle, if you will, in this Verhagen formalism. If you do that, you recognize again a flux that is pierced in exactly this kind of a system. So this forms a geometrical phase, just like the Maharonov-Bohm loop did in a Hermitian system. And this we can use to control interference in this loop, and to basically couple different quadratures at will to each other, and create systems where, for example, the loss quadrature is coupled to a gain quadrature in another resonator. And this gives rise to exactly this symmetry breaking that I was telling you about before, PT symmetric physics, at an exceptional point that we can now, however, control by introducing these fluxes. So these give an extra degree of freedom that in these kind of systems control the non-Hermitian dynamics. Now, finally, if we turn back to our non-Hermitian trimer, also there you recognize these kind of effects. In fact, even in this case, we can recognize the breaking of PT symmetry that is in fact even of a higher order kind, meaning that we see higher order exceptional points and a complex phase diagram here in these kind of systems. And in fact, exactly at this exceptional point, what one also sees is a strong amplification now that we introduced parametric gain that is also strongly chiral. So if you drive one resonator, number one here, you switch on these interactions, you see that an excitation is strongly amplified towards number or resonator 2 here, but in the opposite direction, it is strongly damped. And exactly this is, in a very small system, this kind of non-reciprocal amplifier that these ideas started with. Okay, so that brings me to the end. I hope that I showed you how one can break time reversal symmetry and control this in a very versatile manner to create both Hermitian and non-Hermitian mechanisms that could be the building blocks of topological insulators, but also allow studying a lot of other things. For example, how to control thermal transport in these kind of systems, how to exploit non-linearity in these systems, because it's in fact very strong, and how to maybe apply it to, for example, enhancing sensing as it has been proposed. So with that, I'd like to wrap up and just thank the people that did this work, Jesse and Javier in particular, in the past, John and Freek, my collaborators, both the past ones and also the present collaborators, including Clara, Matteo, and Andreas. And with that, thank you for your attention.
Thank you very much, Ewold, for this amazing talk. And the outlook certainly sounds very interesting. Do we have any questions? If you have any, you can either raise your hand or you can type it in the chat. If you're joining on YouTube, please type them in the chat and we will forward them to Ewold. Maybe I can ask one in the meantime about the squeezing dimer that you showed. Did you also look at collective quadratures? So, for example, x1 plus x2, and if these are squeezed as well?
Oh, absolutely. Yeah, that's a good question. I'm not sure that I don't think I have a backup slide that shows it, but if you want, you can look up the result in the archive paper. We have done exactly that. And so what you see is that there are signatures of two mode or two resonator squeezing, if you will, exactly when in the case where the single mode squeezing is absent. So, and also this you can understand because of the interference mechanism. So you can tune between single mode and two mode squeezing. The PT symmetry, though, is only there for the guaranteed for the case where you have maximal, where in fact you have maximal two mode squeezing and no single mode squeezing. Yeah.
And because I think time reversal symmetry is broken, right? So do you also see some non-reciprocal effects?
Oh, that is a good question.
Squeezing is maybe asymmetric. I think maybe in a collective basis this could happen.
Exactly. What you would need to do is to turn to some collective basis. I'm not so. This is a very interesting question. Yeah.
Yeah, I was just curious. Okay. Do we have any other questions? Maybe I can just ask one and then we wrap up.
Right.
About quite in the beginning when you talked about breaking time reversal symmetry and you showed that you couple two I think two mechanical modes with I think you really one mechanical mode via two optical modes. I think you really need to add the coupling between the two optical modes to break time reversal symmetry, right? Or is it right? Otherwise you could gauge the phase difference away between these two paths.
You mean now when coupling two optical modes to one mechanical? This is what you're saying?
That's what the example you had on the slide, and I think I was wondering if I think you really need to couple the two optical modes.
Okay. Yeah, absolutely. You always of course you can always you always somehow need to close a loop to get a. You always need to close a loop to see any effect that you cannot indeed gauge away. There is still, and in our this Nature Nanotechnology paper, we showed that you can also close that loop in a if you will in a measurement by mixing the signals that you see for both that you receive from both resonators, and still prove that even a single link is how do you say is breaking time reversal symmetry, or is allowing you to break time reversal symmetry.
Yeah, basically, this was what I was aiming at. If there is maybe a really subtle way to So I think this is a bit more subtle because
it is very subtle. You did, and you need to be able to process these signals, including their phases, because you basically need to mix them down and to effectively close the loop. But in the optical domain, if you couple from one optical cavity mode to another that are anyway at the same frequency, of course, the only thing you still need to do is let them interfere, if you will. That closes the loop. And so, depending on how you do that exactly, you create isolation or gyration or another effect.
Well, thank you. Thank you again for this really exciting talk. I don't see any other questions, but I really enjoyed today, and thank you very much, Ewold, and thank you very much, Amir. Before we finish, let me just briefly advertise our next seminar, which is in 2 weeks' time. And we will have Tirth Shah, who will be talking about his work on topological phonon transport, and Ash Clark will talk about the bosonic key type chain and his work related to non-emission sensing. So a lot to look forward to. Thank you very much again, Ewold and Amir, and everyone for joining. And we're looking forward to see you in 2 weeks.
Thank you.
Thank you.